Today's topic illustrates this mission particularly well. Sleep research can involve many different types of information, either about the sleep cycles itself, including polysomnography, EEGs, and actigraphy data, but also about other factors that influence sleep, including genetics and clinical measures. So bringing these complementary data types together can support richer questions about sleep, health, and disease than any one of the data sets could alone. Next slide. However, combining these data sets from multiple studies is only really valuable when the data are interoperable. Differences in file formats, data processing, terminology and vocabulary, annotations, as well as study-specific conventions can make cross-study analysis difficult. So consistent processing, robust feature annotation, common data standards, and harmonization are required to transform these studies into interoperable data sets that are ready for analysis. Next slide. Within Biodata Catalyst, researchers can access sleep data alongside a broad range of cohort and omics data sets. Users with an active dbGaP data use request can access this data through a Biodata Catalyst user project and then perform analysis, run workflows, and collaborate with colleagues in this shared environment. Next slide. And so with that, it's my pleasure to introduce today's speaker, Dr. Ying Zhang. Dr. Zhang is a senior data scientist in the Sleep Medicine Epidemiology Division at Brigham and Women's Hospital and Harvard Medical School in Boston. Her work focuses on making complex biomedical data more standardized, interoperable, and reusable. At NSRR, Dr. Zhang leads several metadata and data harmonization initiatives, including standards for polysomnography and actigraphy metadata, sleep architecture terminology, compositional coding frameworks, and both expert-led retrospective and AI-assisted prospective harmonization. Her current research also explores sleep apnea metabolomics and the integration of multi-omic data with clinical sleep studies. Today, she will discuss NSRR harmonized data and its impact on the scientific community. And with that, I'll turn it over to Dr. Zhang. Thank you for joining us.
Thank you very much for having me today to talk about what harmonized sleep data, the National Sleep Research Resource, NSRR, is bringing to BDC, how it was built, and how to use it. So I'm going to start by a brief introduction on NSRR, why sleep data harmonization is necessary, our approach to harmonize sleep data, and how to find and access those harmonized sleep data on BDC, and end with some practical examples, limitations, and future directions. So NSRR is a NLBI-funded sleep domain-specific data repository. We, different from most of the general purpose data repository, we offer a very bespoke kind of process for data ingestion and sharing, which means we spend a lot of time thinking and working on metadata standardization, curation, QC, and data harmonization. We share mostly sleep data, including polysomnography, actigraphy, and self-reported sleep measures from clinical studies and cohort studies. And now we're also expanding to animal experiments and circadian data. In addition to data sharing, we also share a variety of resources, including tools like open source tools for signal file processing and analytics, trainings and workshops and webinars, and also like the harmonized data as well. Currently, we're hosting more than 50 data sets, and we're still growing. So the first question is, why do you want to use multiple data sets for your research? Using a single cohort, a single data set, you can maximize population technical homogeneity, but at the risk of overfitting. And even with like data split between training and testing or cross-validation, you can only achieve internal validation, and it's hard to generalize findings sometimes. With multiple data sets, you increase the sample size and statistical power, and you can do external validation, and then you can improve the generalizability by leveraging the heterogeneous study populations. then why cross-dataset analysis is difficult for a researcher in general, because there are a variety of sources for heterogeneity that an average researcher will be hard to understand or account for in their project. For example, there are semantic inconsistency, meaning the same variable label might mean very different things across data sets. One example will be AHI, the apnea-hypopnea index. It might mean very different things if the study was done 30 years ago versus 10 years ago. And also in our RAM latency, for example, that's basically an interval between sleep's onset and sleep offset. But in one data set, it might include the wake period, while in another, it might be excluding wake period. And oftentimes it's not clearly described in the label, and it's hard for people to figure out themselves. And then in other cases, different variable labels might mean the same thing. We've seen this actually showing up a lot in our data set that people use sleep time, sleep duration, and sleep period interchangeably, even though there is some kind of consistency within the data set, across data set, sometimes hard to map the concept across data sets. And then because the sleep data, a lot of the sleep data are physiological signal data, the technical inconsistency is another major concern because different devices, software, and algorithms might lead to very different output summary metrics and will be hard to compare across a platform, especially given some of the summary metrics are directly exported from the software with the proprietary algorithms. It's really hard to understand if they are truly comparable from one platform to the other. And then there are also the measurement inconsistency. As I mentioned before, for sleep apnea research, especially because the American Association of Sleep Medicine issued guidelines on how to define apnea-hypopnea events, but that guideline changed over time. They have issued many updates. So it's even hard for a kind of domain expert to kind of keep track of those change in the definition. So that's why a data set done 30 years ago versus 20 years ago versus 10 years ago might be using different versions of that apnea-hypopnea definition. And then for self-reported metrics is another issue. You might use validated instrument versus modified instrument versus a single questionnaire item to measure the same sleep construct. Then it's difficult to compare, a score versus a single questionnaire item across data sets. And then the last category, although this is not an exhaustive list, that we kind of struggle on daily basis is the unknown inconsistency. The situation that you kind of don't know what you don't know, oftentimes due to the missing provenance, incomplete metadata, such as the unclear scoring rules, the missing logic for deriving a metrics, or some inter-site variability that's not well documented, or unavailable software package versions, and so on. So all of this make it difficult for an average researcher to do a cross-data set analysis. This is where NSRR kind of come in with our unique combination of domain knowledge and our access to the data owner or data creator. So this is our harmonization approach for a retrospective harmonization of polysomnography summary metrics. That has a relatively narrow scope because we also have another project led by Dr. Sean Purcell focusing on prospective harmonization of signal processing, which will not be the main focus of today's talk. So just to give a general kind of description of how we approach it, first we need to understand the scale of all those inconsistency I mentioned in the previous slide through metadata curation and standardization. And then we also standardize the sleep terminology so that internally we know what terms we're talking about. Then after all the preparation, we enter this iterative process, starting with identifying a target term. Then we try to understand the domain-specific data generation process, from where and how the data was generated, how it was processed, and how it will be analyzed. Then we assess the major source of heterogeneity along that process on the study level and the variable level. With all those information, then we can go back and refine the target terms. Sometimes we need to widen it or narrowing it or split it into multiple terms. And then we will map the target terms to the deposit data. So this is a slide for our prospective signal harmonization led by Dr. Shampasel. I won't go to too much details here, but here is the URL if people are interested in knowing more about the project. So let's talk about the metadata standardization and curation. So usually we would take the existing metadata from the data owner, usually in the format of lengthy PDF files for the study manual or MOP, and then plus the data dictionary, oftentimes with very minimal metadata. A classic example will be a variable called AHI, and the label would just be apnea-hypopnea index. Then we also generate additional metadata using our own tools. We have our own NSRR metadata intake form, the informed consent form, a REDCap survey form, and also we have a lot of like emails and calls going back and forth, try to understand what the variables are and how they were generated. So we have all those information and we process them on 3 levels, the study level, file level, and variable level. And those information got turned into a variety of different metadata outputs. So here's an example of before and after. The left-hand side, as I mentioned before, is just a simple variable AHI and the minimal labeling. And then on the right-hand side is after our curation, we added the detailed description for the apnea-hypopnea event definition. And then we also added the type of sleep test. This is a type 1 polysomnography, and we also provide information about the alignment with the ASM guidelines. So all those information will help the user to truly understand what this apnea-hypopnea index is, whether it will fit their research need. And also, we deposited this additional metadata to BDC, so BDC users have access to those additional metadata as well. Now, in terms of standardization, as I mentioned before, we found sleep time and sleep duration and sleep period are very confusing terms that people use interchangeably. Then we started to standardize the vocabulary. So here's our set of rules. We define time as a specific point of time versus period is a continuous interval between 2 specific time points, while duration is the aggregated sum of multiple intervals describing a specific state or condition, can be sleep versus wake or sleep stage. One example here, if you look at the 2 yellow crosses, sleep onset, the cross here versus sleep offset, those are the 2 time points. The interval between those 2 time points is a sleep period. It's just a simple interval. While the gray boxes in between, they are the wake period, so-called wake after sleep onset, WASO. So if you take those WASO out of sleep period, that's the sleep duration. It means the interval between the sleep onset and sleep offset while the participant is asleep. So with all of that kind of prep work, now we feel like we can start doing the harmonization. We started with the most commonly used variable AHI. We first mapped out the study level kind of source of heterogeneity, that's the study type. There are 4 types of sleep type, sleep test type, Type 1 and 2, they are polysomnography. 3 and 4, they are the home sleep apnea test. But because the home sleep apnea test doesn't have EEG signals, so technically you cannot name the AHI here. It needs to be renamed respiratory event index. So we split AHI into two terms here, AHI and REI. Then we continue to identify source of heterogeneity, mostly for the definition for the hypopnea events. So we look at the flow reduction threshold, oxygen desaturation threshold, and arousal. So with all those varying components mapped out, we're able to build out the different permutations of AHI and REI. So we ended up with 7 AHI and 3 REI. Was the overall goal is to align them with ASM guidelines. As you can see here, they're, the Chicago 1999, 2007 recommended alternative, 2012 recommended alternative, and 2015 recommended and acceptable. It's worth noting that this harmonization approach is largely semantic harmonization. It's not data-driven. Similarly, we did harmonization on the non-sleep demographic data following the TopMed harmonized phenotype and BDC guidelines. So this is an example of the sex variable. We renamed the variable and also recode the value so that all the harmonized sex variable has NSRR_sex as the variable name, and male, female not reported as the coded value. So how to find those harmonized data? Currently, there are 3 data sets with harmonized data on BDC, the Sleep Heart Health Study, Cleveland Family Study, and Hispanic Community Health Study. All the harmonized data are in a separate data file, and the harmonized variables all contain the NSRR_ prefix. And here's the full list of the harmonized data. We have about 9 non-sleep covariates like age, sex, race, BMI, smoking, and seated blood pressure. For the core PSG variables, we have all the permutations of AHI and REI, together with total sleep duration, arousal index, and a signal quality flag. And then the supplemental PSG variables include mostly sleep architecture and the oxygen saturation variables. So there's one quality measure we would like to highlight here because we think it's important for user to understand the meaning of this variable and how to use it. So for polysomnography data, which should have EEG signal, some participants or some recordings might not have good enough EEG signal, so that the scorer have to use like a default of stage 2 and do not score the arousal. So for those participants, we will flag them as sleep wake only, meaning there's no full staging available, only sleep or wake, versus the rest of the participant do have full staging. So it depends on your research need, you might want to exclude these participants given this quality flag. Now here's a full list of the harmonized variables by dataset. Sleep Heart Study probably have the most harmonized data. There are 34 variables from 9 domains. It has many of those are AHI variables, while Cleveland Family is close, but it doesn't have the oxygen saturation variables. It has 27 harmonized variables from 8 domains. The Hispanic Community Health Study is different from the previous 2. It has the REI rather than AHI, and because it doesn't have the EEG signal, there are not many sleep architecture variables. Also, it doesn't have the oxygen saturation variables, so only 14 harmonized variables from 6 domains. So now that you know what data is available, how to use those harmonized data. Just like any analytics, we recommend doing pre-analysis QC, starting with accounting for the expected cohort difference, meaning you will want to regress each harmonized phenotypes on the core covariates, um, for example, age, sex, BMI. And then once you get the residual, you can quantify the residual cohort effects. For this one, we recommend prioritizing partial R square over p-value because the question is not to answer whether or not the harmonized phenotypes from two data sets are statistically identical, but what percentage of the residual variance in the harmonized phenotypes are attributable to the data sets. If that percentage is low, for example, 1% or so, then it actually supports the design of using it in the pooled analysis, adjusting for data sets, even if the p-value is significant. Then after that, we also recommend to assess the heterogeneity of the association. If you already have an outcome of interest, then you can test the interaction term for the phenotype and data set. If that interaction is insignificant, null, then it's also supportive of using the pooled analysis as the primary analysis. So there are two scenarios to kind of give people a more intuitive understanding. Scenario one, if you use a semantically equivalent AHI, for example, this HP4U ASM15 from two data sets, then you calculated, you quantify the residual cohort effect, and the data set accounts for about 1% variance after adjusting for age, sex, BMI in this AHI, a harmonized AHI measure. Then, and it's supportive of pooled analysis, adjusting for the data set. In terms of sensitivity analysis, you can run a meta-analysis of the cohort-specific estimates. While for scenario two, if for some reason you cannot find the semantically equivalent phenotype, but only something that's relevant or similar, in this case, there are two different AHI, the AASM07 that use 50% flow reduction versus 2015 that uses 30% reduction. They are not the same. In this case, maybe it's a good idea to start with a meta-analysis of the cohort-specific estimates instead. We also did some data-driven diagnostic of the harmonized AHIs. On the left-hand side is just the raw AHI after PCA. You can see like the MESA study and Zebra Health study kind of overlap more compared to Cleveland family. It's slightly more offset, but once you regressed out age, BMI, gender, then they're largely overlapping. And this is just another graph when we did it on a bigger scale to include additional data sets that has the AHI variables. Again, it's reassuring to see, the residual are mostly overlapping. So now let's talk about the limitations and future direction. As you can see, our metadata curation process can be laborious and subjective. And then this expert-led retrospective harmonization is really hard to scale. And then because we use the semantic harmonization, it doesn't automatically guarantee the statistical equivalence. There might be residual or procedural differences, like the unseen inconsistency in the previous slide, things that just not documented, or even us, we cannot tell from just looking at the study manual. And then there also might be real biological or demographic differences. Then because we do the exact semantic match, you might find missingness kind of differ by data sets. because we're not doing the best available kind of harmonization, it has to be exact match semantically to share the same variable name. Also, the harmonized variables may inherit the limitation of the original source data and metadata. If the source data has any quality issues in terms of signal quality, measurement error, misclassification, it will get preserved in the harmonized variables as well. Then in terms of future direction, we are currently expanding our harmonization effort beyond one variable at a time mapping. We are using the expert annotated retrospective harmonization to support our AI-assisted prospective harmonization. We are also doing more data-driven validation, like the one I showed earlier. We're also trying to improve the interoperability with external standards in ontology. And most importantly, we're trying to foster community engagement in developing and disseminating metadata standards, such as the core sleep and circadian common data elements. So before I wrap up, I would like to put a little advertisement here. So earlier in the spring, NSR did a 3-part mini webinar series on CDE, the common data elements, and how CDE can be benefit to the sleep research community. So we are now organizing a working group to develop sleep and circadian research CDEs. So if you are interested, please reach out to me or fill in this online recap form to volunteer to be part of our working group. We welcome people with diverse background in sleep domain or just bioinformatics in general. Okay, so that concludes my talk. I'm happy to take any questions.